I'll go ahead and share my screen here. And hopefully you guys can see this. So first of all, thank you guys all for joining us tonight. We really appreciate that you decided to spend a chunk of your evening here listening to this. My name is Nick. As they said, I work at Pure Storage in the Prague office, and I'll be talking about technical interviews tonight. So before I get started, I'll just mention kind of the intended main target audience of this talk, kind of what we were aiming for when we were preparing this. We were thinking of someone with some programming background, but not necessarily so much experience. Someone, for example, like a student, or maybe you're already working as a software engineer somewhere, but you're less experienced. I think that's the person that will get the most out of this. If your experience level is above that or below that, definitely stick around. I think there will be some value for you, but I just wanted to mention that's kind of the main audience that we had in mind when we were preparing this talk. So let's get into it. So first of all, I think most of the questions, the vast majority of questions that you'll get in a technical interview will fall into these categories. The first category is what I like to call the quiz type. And these are really language specific or technology specific questions. Things like, how do you do this in Java? Or what does this keyword mean in this language? Things like that. The next category is the system design category. And that's kind of problem solving and design at a really high level. Things like the famous interview question, design Twitter for me. That's a system design question. And I think these are more common as you progress in your career and as you interview for more senior level positions. I think you'll see more of these. Although, as Sanisha said, you still see the algorithm type questions at higher levels. But that's what we're going to be focusing on tonight, is the third category, the algorithm category. And these are problem-solving questions at the code level, where it might take a few different forms. You might be writing on a whiteboard, or you might be doing a screen share and someone is watching you write code, things like that. But it all boils down to the same thing, which is problem solving at the code level. So first, number one, please, 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 you have to talk. If there's only one thing you take away from this whole presentation, this is the thing. When you're in a technical interview and you're writing code in this type of situation, you have to be comfortable talking. You have to be comfortable saying what your plan is, saying what you're doing, what you're planning to do next. And I understand that it's not the most natural thing for some people, but luckily it is a skill. With this, I highly recommend that you do practice that. You can sit at home alone and you can write code and you can explain it to your dog or to your rubber duck or whatever, but definitely practice that. And it's easier for the interviewer to help you if they know what you're thinking. And I'll tell you guys a secret. The interviewer is actually looking for reasons to like you. They want you to succeed. Nobody goes into these interviews thinking that they want to fail everyone, because that would be a waste of time. So please talk and make it easier for the interview to help you. The next tip is to, as soon as you finish reading through the question, just kind of repeat it back, paraphrase it in your own words. And this will accomplish two things. Mainly what you're trying to do is just make sure that you understand the problem properly and that you're not going to solve kind of a different problem. But another thing it can do, I would say it's not that common, but I have seen it sometimes, that sometimes companies will ask you questions that are intentionally ambiguous. They're kind of intentionally leaving out some information, and they leave it up to you to figure that out, to ask these questions. And it's in your best interest to figure this out as soon as possible. And this can help you doing that. The next tip is just don't be afraid to write an imperfect solution first. Of course, if you see a problem and you can think of optimized a really good solution, then of course do that. But this is more for the case where you're not really sure how to do it well, or you're not really sure how to optimize it. Don't be afraid to just write like a brute force solution. Don't be afraid to just solve it in any way. And I think you'll find that once you have something there, it's easier to go from that to the optimized solution than just going straight to the optimized solution from nothing. And again, it's easier for the interviewer to help you. Sometimes they can ask you questions that will lead you down the right path. Last tip, just knowing how to discuss mainly time complexity, but to a lesser extent, space complexity. I think a lot of times you'll find that it's really common that as soon as you finish writing a solution to a problem, the very next question is going to be, okay, how fast does it run? What's the big O notation of this algorithm? And so being able to look at code that you've written and be able to figure out the big O notation is going to be really important. So now we're going to get into some common algorithms and data structures. Before we do this, there's two things I want to mention. The first thing is the main goal you should have. So I'm going to be discussing this in the context of job interviews, but I think your main goal, your ultimate goal, should be to learn these concepts and to learn these tools and know when to apply them and basically make yourself a better engineer. And as a side effect of that, the job interviews will become easier as you know these concepts better. The second thing I want to mention is just I have kind of limited time here tonight, so I can't go into too much detail in each topic. I think you'll get the most value out of this talk if you treat this as kind of a checklist or like a study guide. So if I mention something that you're not familiar with, just make a note of it and spend some time later and familiarize yourself with it. And I think that's how you'll get the most value out of this. So let's jump in. So the first one is arrays. I hope we're all familiar with arrays. It's kind of the most basic structure that everyone learns as the first data structure, I think. But I think the point is with every data structure is just to know the things that it's good at and know the things that it's not good at. Arrays, you have really fast access by index. So if you know where your element is in the index, you have constant time to access that index. The things that it's not good at are inserting and deleting, because arrays have the property that they're actually located in one continuous block of memory, and each element is next to the following element. And if you want to insert in the middle of that array, you have to actually shift all the following elements down. So that's why it's expensive. That's why it's your time to insert and delete. However, the reason why I have that little star there is you can insert and delete at the end of the array without paying that price. So if that's possible, you can do that. Another thing to be aware of is the capacity of the array. And what that means is, because they have that property of being in one continuous block of memory, it's possible that if you keep adding to the array, you'll run out of space. And what happens in that case is the array has to be copied to another location. And so just be aware of that. Most languages have a way to reserve if you know how much space you need up front. So just be aware of that so you don't have to pay that cost later on. So the next one is the linked list. What linked lists are good at is inserting and deleting, because the nature of the linked list is each element just points at the next element. So there's not a guarantee like in arrays that they're in one continuous block. They could be located anywhere in memory. So if you want to insert and delete, it's just a matter of rearranging the pointers. So that can be done in constant time. So if you have a situation where you want to be doing a lot of inserting and deleting, you would go with a linked list rather than an array. And also this, to be honest, this is kind of a meme or like a joke at this point, how often this comes up. This question comes up so much in job interviews that I think you just want to be familiar with it, how to reverse a linked list. And even though it is a very common question, I still think it's a good interview question, because if you want to do it in the optimal way, which is, a single pass, a single loop, you have to, there's 3 different pointers that you have to keep track of. And you just have to be kind of careful that the order that you update them so that you don't lose any information. So if you're able to do this in an interview setting, it's demonstrating, first of all, that you understand pointers, but second of all, just that you can keep those things straight as you type out an algorithm, which of course is a very useful skill as a software engineer. So now, hash maps. If you're not familiar with hash maps, definitely take the time to familiarize yourself. Hash maps are so common when you're optimizing for speed. If you're ever in an interview situation and they ask you something like, can you make it go faster? Your first instinct, your first thought should be hash map. It won't always be the solution, but I think you'll find often enough it will be a good solution. And hash maps, what hash maps are good at is the constant time inserting and deleting and searching. However, the reason I have that star there, the caveat is that it kind of depends on the quality of your hashing function. So if you're using kind of a language defined, like a built-in hash map in whatever language, you probably won't run into this problem. But if you have your own hash map and you've made the hashing function, you just have to be aware that it has to be a good hashing function. Otherwise, you won't get this constant time performance. So moving on to stacks and queues. What stacks and queues are able to do very well is very fast inserting and deleting. There are some constraints, but the reason you would use a stack or a queue over, say, a hash map is because a stack and a queue maintains the order of the elements. Whereas a hash map, for example, you can tell whether an element is there, but you don't know the order that they were inserted. A stack and a queue has very fast insertion and deletion. Yeah, the strength of the stack and queue, like I said, is that very fast insertion and deletion, and it maintains the order of the elements. For the stack, I mentioned the stack of books. For the queue, I like to imagine a queue of people in a supermarket where you can only add people at the end of the queue and you only remove people at the beginning of the queue. So depending on the problem that you're solving, this can be an appropriate a tool to use. And yeah, now we get into a few algorithms. So breadth first search and depth first search are mainly graph traversal algorithms. However, there's an example of this later. You can apply it to other types of data, but mainly it's intended as a graph algorithm. And the difference between breadth first search and depth first search is just the order that you visit the nodes. I'll kind of demonstrate that here. So in breadth first search, you're going kind of level by level, where you just go all the immediate children. You would process in this case 1 and 2 here before you go to the children of these nodes. And I like to imagine breadth first search as if you can imagine a map and there's cities connected by roads. And if you're starting at one city, you can expand. You can go to all the cities that are just one road away from that city. And then in the next round, you can go one road away from these cities, and you expand in kind of that uniform way. Whereas depth first search, on the other hand, you're going all the way. You keep going down until you reach a child node, a leaf node, a node that has no children. And from there, you kind of unwind. So in this case, you go 1, 3, and you unwind, and then you go 4, and there's no children, so you kind of unwind, and you kind of process it that way, where you're trying to reach the leaf nodes first. So the next topic is sorting, and I'm not suggesting that you should go and memorize for example, how quicksort works or merge sort or any of these, what I'm suggesting is that you just be aware that this is a tool that you can use, that sometimes it makes sense to kind of pre-process your data to optimize later steps. And so know the cost of sorting. The cost is n log n. And just know that, yeah, sometimes it makes sense to pay that cost to optimize future steps. For example, if you want to use binary search. Quick description, if you're not familiar with binary search, the idea is that if your data is sorted and if you're looking for a certain element, you can eliminate half of the elements in each round based on looking at the middle element. So for example, in this example, if you're searching for, let's say 2, you can look at the middle element, which is 21, and you can say, okay, 21 is bigger than 2. So not only can I ignore 21, I can ignore everything after 21, and you can ignore this half of the array. And then you would do it again. You would look now, 5 is the middle, and you would say, okay, now I can ignore everything 5 and after. And you can see that by just examining a few elements, you're able to actually find the one you're looking for. And this performs in log of n time, and that's just because you're reducing by half each time. So that's why it ends up being logarithmic. Another topic to be aware of is recursion. A recursive function is just a function that calls itself. And ideally, if you're trying to solve a problem with recursion, the first thing you want to do is identify the base case. You figure out when the recursion stops, basically, when you stop calling yourself. And the recursive function should be pretty simple. I think most of the time you want it to be not more than a few lines. There are some downsides to recursion. And for example, in my personal experience, I've worked at a few different places where recursion is kind of discouraged. It's kind of frowned upon because usually it's just not the best way to solve the problem. It is an interesting concept. It's a good thing to know, but just realize that it's often not the best way to do it. For example, one reason why is because it's difficult to debug. If you can imagine putting a breakpoint and your call stack is just many instances of the same function, it's a nightmare to try to figure out what's going on there. And in many cases, I think you'll find that if you have a problem that can be solved with recursion, it can often be solved in a more efficient way with dynamic programming. And dynamic programming is a similar idea to recursion, where you're breaking the problem into subproblems and you're using the answers to those subproblems to solve the overall problem. But unlike recursion, you're actually storing the answers to the subproblems. And recursion, as soon as the call stack kind of unwinds, everything is lost. You're not saving anything. With dynamic programming, oftentimes you're caching it, and you could even have an optimized solution where you kind of pre-calculate everything, and then when you query it later on, it's just really fast.
I can see, Nick, another question from Marek. Okay. Can we have recursion without base case?
No, I think by definition you can't, because the recursion, it would just keep calling itself infinitely. Like the base case just means the case where you stop calling yourself. So you have to have that at some point. Otherwise, it's just gonna keep calling itself infinitely. So these are just a few final topics or ideas that I wanted to mention. These come up a decent amount in interviews, but maybe not as common as the other ones. Heap and tree are two nice ones. There's a few variations of these, but just you don't have to know every single one, but maybe just know the general idea, the general structure of a tree, and the general property that most operations are going to be logarithmic, just because of the nature of the tree that it's kind of dividing things in half each time. Another interesting structure is the try. And I would say that it has kind of a limited use case, but it is useful in some situations. Same with skip list. I would say the value is a little bit limited, but it's good to know. Also, a few other topics that are common in interviews, regular expressions, strings, bit manipulation. These are just things that they're good things to know in general. They're useful in your day-to-day job. And it's definitely worth the time. If you're not that familiar with, for example, strings or bit manipulation, then in your language of choice, just go and practice the common operations for strings you would want to practice. You would want to be able to concatenate, call substring, things like that, and get a certain character, that kind of thing. For bits, you would want to do the kind of logic operations and or these kind of things, and also know how to shift and know how to use bit masks. So now we can get to the fun part. These are a few example questions. I will say that every single one of these examples is a question that I have seen in a job interview. Not at Pure, I have to give that disclaimer. I did not have these in the Pure interview, but I have seen these at some point. So let's get into it. So the first question is the Fibonacci question. For anyone who's not familiar with the Fibonacci sequence, it's defined as the first two elements are 0, 1, and all future elements are just the sum of the previous two elements. So I hope you can see the mouse. I'm kind of using the mouse to point. This one is the sum of these two. This one is the sum of these two, etc. And so what we want to do is we want to make an algorithm, make a function that gives you the nth Fibonacci number. Maybe we can make this a little bit interactive. If you can think of kind of an algorithm or a technique, why don't you write it in the chat? What might be a good way to solve this? Let's see, where'd the chat go? I actually can't see the chat. Oops, sorry, I gave it away.
I can see one answer is recursion, another one dynamic programming.
Yep. So yeah, so you can do it both ways. This is what it might look like if you solved it with recursion. So in this case, you have the base case if n is 0 or 1. By the way, I have to mention this is pseudocode. I'm not checking if n is negative, for example, but I hope you still get. I hope you can still appreciate what I was getting at here. So if n is 0 or 1, you return n. So fib 0 gives you 0, fib 1 gives you 1. And for higher than that, you would just call recursively fib n minus 1, fib n minus 2. And this might look at first glance like a decent solution. It's nice and clean. It's just a few lines. But if you really examine it, you'll see that it's actually not a very good approach. And the reason is, for example, consider what would happen if you called fib 10. You would call fib 9 and fib 8. This fib 9 would call fib 8 and fib 7. And what's actually happening is you're calling fib 8 here and fib 8 here, but you're not actually storing that. You're just duplicating work. And this is kind of the nature of recursion, that as soon as you unwind, as soon as you find the answer, you basically lost all that information. And so this is actually a polynomial time algorithm, because you see that every call results in 2 calls, and each of those results in 2 more calls, and you're not sharing any of that work. So actually a better solution.
Actually, there are 2 other ideas in the chat. I don't know if maybe it's there. So I see from Kirill, iterative approach. Then from Dawit, I see memoirs. And then I see another one, fast inversive square root.
Fast inverse square root. I think that fast inverse square root is I suspect that is a joke, but But the memoirs is the dynamic programming. You can also do it iteratively. You can just kind of do the math and do it iteratively. But this is what it might look like, the dynamic programming approach, where you actually start with an array 0 and 1, and you're appending. Again, I have to mention the capacity issue. So you could reserve, if you know, for example, you're going to calculate 1,000 elements, you would reserve 1,000. But you're just building the array. In this case, you're adding one. And I have it set up this way with the initialize function because that's closer to what you might see in a real life situation where you basically pre-calculate all these numbers and then your fib function is really fast. It's like just one array access. Depending on the constraints of the problem, you might have to put this in here, but that's okay. That's still a linear time because it's just one for loop to calculate that, that sequence. But yeah, this is what it might look like for dynamic programming. So let's move on to, this is the next question. This question is called toSum. If you're familiar with a website called LeetCode, this is actually question number 1 on LeetCode. So very cool. So in this question, you have an array of integers and a target integer. And what you're trying to figure out is if 2 elements of this array can be added together to get the target. And so in this case, if you got 9 as the target, you would return the 2 and the 7. So index 0 and index 2. What might be a good way to solve this one? I'll show, maybe first I'll show kind of the brute force, the initial approach, and then we can ask the chat what might be a way to improve it. So this might be your first instinct because you're basically, you have to, pair these numbers up. So your first instinct might be to basically loop through twice, loop through all the numbers and then loop through again, starting at the next number, and basically check if all these pairs of numbers add together to get the target. And this is an okay solution. You will get the right answer, but I think we can do better. What data structure might we use to make this faster?
So I see from Narek hash set. That's one answer. Then I see another answer, HashMap.
Yeah. Then
another one, object, key value.
Yeah. So that's all kind of saying more or less the same thing. So yeah, the answer is to use a hash map. That would let you solve the problem in a single loop. So in this case, what you would do, and it actually has to be, in this case, we want the indices. So we have to actually use a hash map, not a hash set. But if you were just basically, if you wanted to return true or false that you can make those sum, then a hash set would be enough. But anyway, what you would do is you would loop through all the numbers once, and you're checking the hash map for the difference of the target and your number. So in our example, if the target is 9 and the current number is 2, you would be checking if the map contains a 7. And if the map does not contain a 7, you're adding 2 to the map because that's the current number. And then you would continue on, and hopefully later on you would reach a 7. And when that happens, you would check the map contains a 2. It does. Sweet, we're done. And this turns out to be, what would be the runtime complexity of this? So you have one for loop. So that would be n. And then inside here, you're checking if the map contains an element. That's constant time, average case. And then you're adding to the map. That's also constant time. So this whole thing went down from n squared to n, which is great. So now let's suppose you're in an interview setting and you get asked, okay, you found a really fast solution. Now let's suppose we have a target platform where memory is really expensive. So we want to implement a solution where we basically minimize the amount of memory that we use. what would we do? And we can, maybe we can ask the chat what we can do in that case.
Sort the array, that's one. Two-pointer method, another one. Probably sort a sequence.
Yeah.
Bigger and smaller indexed, and traverse it in a single pass.
Yeah. So what I have here is sorting. I'm interested to know what the two-pointer approach is. To be honest, I'm not familiar with that. So maybe there's a better way to do this. But this is what I wrote when I was preparing this, which is sorting. So once you sort the numbers, which costs n log n, you can iterate through one time, and basically you're doing binary search. And there's, because of the nature of the sorted array and the target, there's ways that you could optimize this, but I just have kind of a really quick and dirty approach. But what you're doing is you're looping through once, so that's n, and then your binary search, which is log of n. So you have n log n plus n log n, which is conveniently n log n. But I'm curious about that two-pointer approach. I wonder if they have a better idea than me, which is totally possible. So we can move on to the, this is also kind of a joke in the industry because it comes up so often. If you're not familiar with this question, the idea is you have a string with just these characters, and you want to make a function that basically determines if the parentheses are arranged in a valid way, meaning they match up and there's no extra ones, that kind of thing. And they can be nested. You could have many nested parentheses. That's fine. It's just they have to match, and there have to be like a pair of them, not just one. And this is a question where choosing the right data structure just makes your life so much easier. So what kind of data structure do you guys think would be good for this kind of question? Let's ask the chat.
I see stack. Everyone says.
So everyone. So maybe I guess everyone has already seen this question, or maybe everyone is smart. But yeah, that's correct. A stack. So the key is realizing that as you're going through, as you reach these opening brackets, all you have to do is continue on. And when you reach a closing bracket, you only need to compare it to the most recent opening bracket, which fits that pattern of a stack, the last in, first out. And so let's quickly calculate the runtime complexity of this one. So you have a for loop, which is O of n. This comparison is constant time, adding to a stack, also constant time, checking if the stack is empty, constant time, removing from a stack, constant time, and then another comparison, which is constant time. So even though there's a lot of lines here, this is actually just a linear time algorithm. And that's because you used a stack. So nice job, everyone who said stack. So we can use, I think this is the last question I have here. So this one is called autocomplete. If you imagine you have a dictionary of words, in this example, we have a very small dictionary, 4 words, and you want to be able to be given a prefix, for example, this BA, and you want to get back all the words that can be auto-completed from that prefix. And so in this example, you would get back banana and ball. This is another example where the data structure makes it very easy. I think this is, I hope this is a little trickier than the last question. So let's ask the chat one more time. What data structure might you use for this one?
I think they saw your question coming. The answers were already coming in. So we'll use a suffix array or a trie.
Yeah, try.
And then try again.
Yeah, that's exactly right. We have a smart audience today. So Yeah, that's exactly right. So this structure is called a trie, and the key is for words that share letters, you're sharing the nodes. It's kind of a graph-like structure. So you're sharing the nodes in the graph. And so after you construct that trie structure, when you're given a prefix, all you have to do is traverse, according to that prefix. And from this point, for example, using BA, all you have to do is depth first search. So again, depth first is the one where you're going all the way to a leaf node with no more children. And so you would go ball, you add that word, you would kind of unwind. And if you had more BAL words here, you would add them here. But in this case, we don't. So we unwind and we get banana, and we would add that to the results and then unwind again. And if we had more BAN words, of course, we would add them. But in this case, that's all we have. So yeah, good job, guys.
Maybe one more comment.
Yep, sure.
An interesting exercise is for speeding up the decode of a Morse code.
Oh, I've never heard of that problem. So yeah, I can't comment.
Right.
Yeah. Okay. No, I've never heard of that problem, but yeah, I guess that sounds interesting. So that's all the questions I have. I just wanted to leave you with a few final thoughts. Like I said earlier, this is a skill. And so the more you practice, the better you'll get at it. They have if you're not familiar with these websites, definitely check them out. There's a lot more. I think there's like at least half a dozen of these websites, but the idea is on these sites, you can go on and it will present you with problems, and you can select what language you want to write in, and it will let you write code right there in the browser, and you can execute it. It will run against unit tests, and it will tell you if it worked, if it didn't work. And it's a very useful tool for practicing these type of problems. It's also really useful if you want to learn a new language. For example, earlier this year, I wanted to teach myself Python. So I used these websites to just write some Python code without going through the hassle of installing anything or downloading anything. It's just a really easy way to write some code right there in the browser. So definitely check those out. Lastly, I hope this doesn't come off as too cheesy or anything, but if you fail an interview, of course, try to learn from it. Try to, if you can remember the questions, try to go over them and think of maybe there was a better way to solve them, that kind of thing. But at the end of the day, don't stress about it. It is a very human process, so it's not perfect. Sometimes you can do a lot of things right and it still won't work out for you. And that's just the way it goes sometimes. And also just be aware that for companies, from the point of view of a company, a bad hire is much more costly than missing out on a good hire. So if you go through these interviews and the signal is not clear, if they're saying, well, he might be good, he might not be good, or she, and they're not too sure, they're not going to give you the benefit of the doubt. They're going to err on the side of caution because it's more costly to make a bad hire. So just if you fail an interview, don't stress about it. Keep practicing. You'll get there. Thank you guys for watching. I definitely appreciate you giving us your attention tonight. So yeah, thank you.